Right, good evening. Thank you all very much for coming. Thank you very much for coming. So today is the third Brain and Mind event this term, this year. Will be on touch and the brain after sound and the brain the previous term. Today's going to be a little bit special, and that's going to be a hybrid event with the Medical School Hamburg. We have one of our speakers, Patrick Haggard, here with us in Oxford. Two of our speakers will be in Hamburg together with Anita Avramitidis, who, with Dr. Dauker, Mike Glitch, and myself, organizes these events. So in 1 minute, Hamburg will take over and do the proper introduction to this event. I just wanted to welcome you all here in Oxford before we do that. We'll have two talks, then a bit of a Q&A, then there will be some tea outside, then the third talk, and some more Q&A. So that sounds worryingly like Hamburg wants to be talking instead of us, so I'll pass over to Hamburg now. Thank you very much.
Okay, greetings, sir. Greetings from Hamburg. We are in a room overlooking the Elbe Delta, and it's a beautiful sunny day. And it's shining in. We've had to close the blinds, but we can see the sun shine. I hope the sun is shining for you in Oxford, and we have the perfect synergy for our collaboration. It was 1 year ago this month that I was last in Hamburg hosting this event. And that time, our topic was delusion and the brain. As Barnaby will have already explained, for the past 3 years, Brain and Mind has been run in collaboration with the medical school here in Hamburg. And in the past 3 Trinity terms, which is the spring term, I have hosted this event from Hamburg. Before I begin my true introductory remarks about tonight's topic, I want to thank the medical school here in Hamburg for their generous support for these events, and I also want the principal and governing body of St. Hilda's for its support. And a very big thank you must be given to our IT teams, both in St. Hilda's and here in Hamburg. We usually manage to have some technical glitches, and I am quite have a few tonight, but I very much hope that we can iron these out and that you will be patient with us. Because I hope you'll agree that it's worth it so that we can have a collaboration like this. Now, collaboration is what this event is all about. As those of you who are regular attenders will already know, these events are about intellectual collaboration between neuroscience, psychology, and philosophy. But perhaps it will be a few some of A-level students who attend. And may I extend a warm welcome from Hamburg, any A-level students in Oxford may be attending tonight. These are students who are pre-university, and we invite these students from around the Oxford area to come and attend these events. I very much hope younger students will enjoy the talk and enjoy the opportunity to experience a little bit of university life. The idea behind these events is not to coordinate talks, but simply add those working at the cutting edge of their discipline, how their discipline seeks to understand a particular phenomenon identified for discussion. What we hope is not how different their phenomenon can be from those who are thinking about it and studying it. And for those who are thinking about future study, we hope that it will expand your intellectual horizons. This academic year, we've chosen to think about the senses. And each term we've concentrated on exploring one of the 5 senses. In the first term, we discussed taste. Okay? In the second term, we discussed sound and brain. And tonight, touch. And and the brain. Now, to those of us who are unimpaired, vision will be the dominant of our senses, with taste, sound, hearing, and touch, sometimes a little satisfied. But each senses is important to understand in its own right. Touch is arguably one of the most complex to understand. While the other senses have a particular organ associated with it, the eyes for vision, the ears for sound, alike, touch is something distributed across the whole body, although we often think of it as hands, fingers. Furthermore, touch is centrally involved in our active exploration of the world around us. So it's involved in our, because of the features of touch, it's proved difficult to so much as define a sense of touch, to say what exactly counts as touch. And of course, understanding what counts as sense of touch is a very first step to touch, and the knowledge touch. Having said that touch is complex knowledge, I am going to stop my introduction and hand over to our speakers to tell us about this complex phenomenon. Perhaps by the end of the evening, we'll have a better sense of just what the complexities are involved in understanding of touch. Our first tonight will be in the perspective of neuroscience. Our speaker is Prof Hamburg, Ulf Baumgärtner. He is Professor of Physiology in the Medical Faculty of the Medical School in Hamburg, and his research has mainly concentrated on pain for the brain. The title of his talk tonight is Neuroscience, but Neurophysiology is emotional.
So, can you all hear me also in Oxford? Hopefully. I just continue. So, as kindly introduced, my background is physiology, and I studied medicine here in Hamburg, and so the aspects I'd like to shed light on is more or less, some electrophysiological evidence about the pathways, receptors in the skin, and perception in the brain, and I will briefly touch on the emotional aspects that are related to touch under certain circumstances. So, trying to move forward here. Okay, this is just illustrating different aspects of touch. Touching, in fact, in Europe we wouldn't say this is a football. In America, this is a football, and you can touch or explore objects by distance of touch without looking at them, by means of exploring the texture of this glass, for instance. You are also sensing at the same time temperature. On the top image, you can see that really small protrusions, like millimeters or less, can detect on the surface. You can use this for reading if your vision is impaired. And the social aspect are if you touch yourself, or some beloved person touches you, kisses you. This can be very soothing and nice. And in the image below is somebody else, like a boss is touching a female co-worker. The same touch can be discomforting or discomforting. So it depends on the surroundings, how you interpret touch emotionally. So next, please. So, okay. Can I somehow? Okay, now it's working. Okay. My topics will be first mechanosensitivity of the skin. We'll see what do we have in the skin. Of course, on the way to the brain, we have to pass through the skin. And we have different receptors in the skin, obviously for different functional aspects of touch. And we have receptive fields. We need to talk about what is the receptive in the brain. and how we can perform complex pattern recognition, and how we detect the direction into which stimuli are moving on our skin, like when an ant is walking our arm, how can we feel in which direction it is walking. So these are complex of activity reaching the brain. In the end, to the affective part, so has been known for a long time that also some nerve fibers which are more or less exclusively transmitting sensation temperature, also part of these can convey tactile information, and the cortical representation of these efferents is quite different from the regular touch representation of the brain. Now here we see a set of different sorts of skin, the universe of hairless skin, which in fact is only sole, foot, and the palm of the hand, and the rest is hair skin, obviously, because potentially or actually hairs. And you see that there are quite different receptors. The exact meaning and function is not really important, but since we have so many different receptors, there must be some functional differential properties. We might have that, so we have just one receptor for touch, but a couple of them. And when we look at this set, we see here on the bottom line where it says stimulus, a ramp that could be a touch, a finger, indenting on the superficial part of the skin, then the stimulus is staying there for a certain time, and then the finger is lifted off again, then it's over, and on top of that we see electrical responses of different receptors. So the Meissner receptor, for instance, is only discharging when there's a change in the surroundings. So when the stimulus is setting on, when the finger is lifted off, and while the stimulus is continuously there all the time, it completely stops. And these sort of receptors are called rapidly adapting receptors. Adaptation means they cycles after time when the state constant. Still there, but the receptor doesn't respond anymore. Then there are other receptors like Bruchel or Bini receptors, and they continuously fire as long as the stimulus is there. Obviously, when you translate this into perception, the latter ones, who are discharging all the time, they are really transmitting the information of continuous touch, as the other receptor, the adapting receptor, only coding differences for change. What is the fastest change that there is by means of touch? That's vibration. So that only important when there's the change upside onwards, not only every 6 spots. And you're only interested of 2 different points of the curve, and use it much, you can decode at much higher frequencies, and the optical frequencies where such corpuscles are more sensitive is around 100 or 200 hertz. So 200 touches per second, and by these and the intensity, there is a micrometer where the skin is indented by the thousands of a millimeter, so they're very sensitive. And the cables connected to these receptors are typically thick cables conducting very fast. These are the class of these fibers is a beta fibers. And all this has been recently received at some interest and revival, since the Nobel Prize has been given in 2022 for medicinal physiology to Arun Bhattacushan and Hilda Julius, did publications on receptor property. One on mechanical receptors, and the thermoreception. Now we come to receptive field. What is the receptive field? The receptive field is can go back. When you look at the skin overlaying the receptor endings, you can imagine that when you directly on top of the receptor move your finger or put something on the skin, the receptor will respond, and when you go far away, it wouldn't respond. And then you can identify where the receptive field is. When you put a calling electrode to a single nerve fiber, which is a single cell, in fact, you can use a search stimulus, the periphery, for instance, the hand, and see what area, where this nerve fiber is responding and to which sort of stimulus it is responding. So then you can see how big this receptive field is and to which stimulus the nerve fiber is responding. Then characterize the nerve fibers. On the right, you see that there are some nerve fibers, all receptive fields with more or less high density, especially on the hand. And here now, what you will hopefully see or also hear a video. What is shown here, this is a real-time map of receptive fields by my colleague in Mannheim, Martin Schnells. And when you remember the electrode, which is with the nerve into the nerve fiber, is below this black tape, the arm, and now he's mapping the receptive field with his finger. And I wonder whether the video is working. How it starts, as you see, he's moving the finger, and the discharge is connected to loudspeaker. And as you all know, when you know your body surface, of course, by means of discrimination of a different number of spots touching your skin at the same time. And this is what you call two-point discrimination. You can use a scale or what you call a compass, two needles, and in some areas you will recognize this larger distance as two stimuli, and in other areas, for instance, when you test them on your upper leg or your back or trunk, you'll see that even when the needles are apart by 4 or 5 centimeters, you only detect them as one stimulus. So when you touch your fingertip or your lip, then you can draw through Y steps. Here we see blue is the receptive field, and red, pink would be the second order neuron connected to the first order neuron. Here's another neuron connected to 2 receptive fields. So on the left, blue is one large receptive field, equal to a neuron. Right, 2 receptive fields, smaller receptive fields. 2 stimuli occur at the same time. The large receptive field is at the same distance to 2 receptive fields. And of course, in one case, detect, it will not detect that one stimulus in this receptive field, because it's yes or no. And in the second case, there are inputs from 2 cables that that's 2 stimuli. Always says E is given be on different receptive fields, but to be able to separate them. Hence, the background, why the spatial resolution on touch line, hence on the size of receptive fields, so when they are small, and when the receptors are densely distributed in the skin, you'll be able to have a good 2-point discrimination. Now, this knowledge, you don't have to acquire this during your life. This is what you know when you're almost newborn. As seen here, this little guy by the name of Max, when he was, I don't know how young, for the first time touches a kiwi with his little hairs on his first introduction. He uses his hands and then put it to his mouth, his tongue and lips. It was my son quite a while ago exploring his first kiwi. Now he's 1 meter and he. And now you can, how do these signals now reach the brain? And this is illustrated here. In fact, we've been talking about black fiber pathway. As you can see in the tip of the finger here, This could be a Meissner or Merkel corpuscle. This cable, let's say a nerve fiber, could be a beta thick fiber. Then there's a wave, the spinal cord, or the column, develops in some area in the brain, or the primary sensory cortex. This is for touch and position sense. And there's a red pathway with different fibers in the periphery, very thin fibers, called T fibers, and see there's a different pathway in the spinal crossing immediately after entering the dorsal part, and then different tracts. It also reaches the thalamus and also different areas in the brain, like the sensory cortex as well, but the hippocampal insular cortex, and medial structures like the cingulate cortex. These latter structures are closely connected to the emotional system, the limbic system, and since you think of it, these skin fibers typically convey thermal reception, so temperature and perception. These stimuli, of course, also has a very strong emotional component. Now, when you look at the cortical representations, we are now the primary sensory cortex. Most of you will be aware that there's a map of the body, in fact, of primary somatosensory cortex, which has been determined more or less originally by one person, Ira Penfield, in the 50s, at McGill University in Montreal, Canada, who was a neurosurgeon, and did electrical stimulation of all different brain areas in the sensory cortex, and the awake subjects, patients that undergo epilepsy surgery, basic surgery, were able to tap on how it's tingling in my foot and feel something in my hand, and this is how it mapped this cortex. And when you look at the presentation of the size of the body areas, you see that its proportions are a little bit distorted. The way that the hand and the base of the lips and tongue is represented in an oversized manner. And why is it the case? Because in these areas we have a high density of receptors and coming in from the lips and the hands instead, and they occupy a large area in the sensory cortex, whereas trunk or forearm, whatever, is relatively small areas. And now you can ask yourself, is this a representation fixed forever for all your life? No, in general the cortex is very plastic. This is illustrated here in this monkey experiment. That's a macaque monkey. The board looks a little bit strange, so it's no primate. And on top, you see on the left the paw of the monkey, digits numbered in 4 and 5. And on the left and on the right side, you see the representation in the sensory cortex, also labeled with red positions D1 to D5. That's the baseline condition. And there are 2 experiments involved finger number 3. And after some time, they were re-examining wiring to the cortex and saw that the former area D3 is now missing, and the neighboring areas, D4 and D2 more or less have invaded and taken over the former area of D3. The area is shrinking and taken over by adjacent areas. So if the contrary happens, and so if 2 fingers, the aspect now, are stimulated with a little sharp-pointed wheel all the time, a couple of days, for minutes, hours, and during successive sequence of days. So these 2 fingers, D2 and D3, are stimulated continuously. This causes an extension of the receptor, of the representation areas in the brain. This area D2 and D3 have grown larger and made its extension. That's what we call use-dependent plasticity. So brain areas that are rarely used are are shrinking. Areas that are frequently used are increased handling. And this is one of the bases for rehabilitation. So if you look at the stroke, for instance, its brain areas get damaged, then other areas adjacent or remote may be able, at least in part, to take over these functions. Now we are looking to complex pattern recognition in cortex, or first in the peripheral coding of the nerves, and then later in the cortex. So what we see here, this is again, on the left, see this nerve fiber recording. Recording electrode inserts the peripheral nerve, and some stimulation applied to the receptive field, in that case of unfinger. And so you see the cylinder with the imprinted letters A, B, C, D, E, and this is now rolled continuously over the receptive field, and then the cylinders moved a little bit further downwards, and what you see is the discharges line by line. So this is the first line, that's second line, this is discharges when the action potentials occur in the recording on the peripheral nerve. So you can almost read the letters by this presentation here. When you now record this from the brain area 3D, which is one area in the sensory cortex, almost the same. You can almost read the letters from discharges when they're written after Latin on sheet of paper like this. However, when you look into area now, different brain area in this 3 cortex 1A or 1, there's hardly anything that you can see. So this area obviously is different meaning. And this area, when now we are recording from area 1, different brain area, and when you're giving static stimuli to this receptive field, there's almost no discharge to the right. And their stimuli are moving within this receptive field, so there's a touch. And while the contact effect probes move different directions, we see that there's some sensitivity for direction. So especially when stimulus moves from bottom to top in that receptive field, there's a strong discharge, as in the other direction, there's no response whatsoever. And how can this be obtained? This can be obtained because central neurons wire to a number of peripheral neurons with a number of different receptive fields in a row. So the central neuron has more information from the periphery. And here we see the orientation of the pink receptive fields onto another, and their excitatory field responds to. So they discharge in this receptive field, there's a touch, and adjacent to that there are inhibitory receptive fields also exist, and when stimulated there, the response is inhibited. When we now have something like COM moving from upside, from the upper part to the lower part, you first have excitation, and then we have inhibition, and this causes the discharge here and inhibition after that. We move the stimulus from upside down, there's no response whatsoever anymore, and this is because typically the inhibitory activity outlasts excitatory. That's a general rule. So this is how direction can be perceived. Okay, so the last aspect now, I'm coming now to the effective part. It has been known for a long time, as I've already said, there's some strange type of sleep fibers, unmyelinated sleep fibers, which are responsive of the light. This has been known for 80 years, and recently it has gained attention again. And so there was one patient, 2 patients in fact, and one investigated here, he's from Norway. who had, after neuropathy disease, damage to their thick fibers. So all the thick myelinated A fibers were gone, and all that was left was thin or unmyelinated fibers, type C. And their perception, patient perceptions, was normal touch was on, but temperature affection, transmitted the thin fibers, was preserved. Also preserved now, and there was a testing here with a moving brush over different areas of the skin, was that the detection of these brush stimuli was 100% normal on the forearm, also on the dorsal of the hand, whereas vibration sense, which definitely sucks the thick fibers, was completely lost. So there seem to be two pathways conveying touch. Okay, so in the end, we see of different cortical regions. For normal subjects, strong activity in the sensory cortex, and in the patient, there's no activity in the sensory cortex, but the insular cortex. So previously, also which is reached by temperature sensation, this is wired to the emotional system. And this is illustrated in this review. So we have obviously two touch pathways components, or the discriminative touch pathway, which I'm in the first part of the talk, the latter by the first can term sort of emotional or affective touch pathway. Though in the end we can say, when we have to amend something to this sketch here, the red pathway also conveys affective touch. And with that summary, which I already gave you, and I think this is a well-known picture, the touch by Michelangelo. Thank you very much for your attention.
I'd like to ask Oxford if everything is all right.
Everything is
Perfect. No, it's not. Very good. We're now going to continue straight on with the second of our talks before I take a few questions on this talk. And then after that, when we have the questions, we'll break for tea and coffee. So I'm delighted with us in Oxford, Professor Patrick Haggard. Professor Haggard is Professor of Cognitive Neuroscience at University College London, where he leads action and the group. There's two main themes. The first is the cognitive neuroscience of voluntary action, and the second is the representation of one's own body. Professor Haggard is a psychologist who spends much time in dialogue with philosophers, and this, combined with his research interests, makes him the perfect speaker for us in psychology this evening. Professor Haggard's talk is entitled, Is Touch Being Spatial? And now we're going over to Oxford, and I believe that everything is going to go.
Yeah. Good. Okay, thanks very much for inviting me to talk, but it's a pleasure to be here and a pleasure to have all the colleagues joining from Hamburg. I'm going to talk for about 20 minutes on whether the sense of touch is really spatial or not. I can go quite quickly because Ulf Baumgärtner has already presented quite a lot of the slides that I was going to show. I'm going to see if I can get a laser pointer. That would be helpful. Okay, so we've seen that there are multiple different receptors in the skin, and I'm going to be talking particularly about one receptor, which is the Merkel disc receptor, which is the one that responds to steady, sustained pressure on the skin. So when objects touch your skin for a prolonged period of time, those are the fibers that give us fine detail about exactly what is touching us and where it's touching us. And we've already seen that these are distributed particularly in the fingertips, and that they respond continuously when a stimulus is continuously touched to them. And we've seen that there's a projection of these peripheral receptors into the somatosensory cortex, which roughly explains how good your sense of touch is. It roughly explains your tactile resolution. The question really is, how do you perceive space through your skin? So the nature of spatial perception is an old question in philosophy and in psychology. What is space? How does it work? How do we perceive it? Is it something which is out there? Is it something that our minds construct for us? It's an old question. And there are basically two ways, as far as I can tell, in the history of psychology and neuroscience to solve this question. The first one is to think of space as a matter of a map. And we've already heard from Ulf Baumgärtner's nice presentation how neurons in the peripheral nerves have receptive fields. Here are multiple receptors in the skin, and you can imagine that there are receptors distributed throughout any given region of skin. Here we happen to be looking at the palm. And these receptors will all send afferent fibers to the spinal cord and then up to the somatosensory cortex. And if the relative positions of different receptors in the skin are preserved so that adjacent neurons in the adjacent receptors in the skin project to adjacent regions in the cortex, then the brain has a map of the body, the brain has a map of space. So the problem with this textbook idea is it seems really circular because it's seeking to explain spatial perception on the skin by referring space here to space here. Okay? So it's kind of deferring the question of how space perception works. And it has a bit of a Cartesian theatre feel about it. So Cartesian theatre is a concept developed by Daniel Dennett to explain to describe the way that many of our theories about how the mind works contain the obviously incorrect assumption that there's a little man in our head watching the screen formed by the back of our eyeball, and that somehow our vision works because there's somebody inside our head looking at our retina. This is not true, and it's obviously not the way, for example, that vision can work, and it probably can't be the way that touch works either. So if we're able to perceive, for example, the shape of an object touching our palm, can it really be simply by transferring the information from the spatial arrangement of the receptors on the skin to the spatial arrangement of neurons in the cortex? Is that really an explanation, or is that just replacing one spatial layout of receptors with another spatial layout, that of neurons? There's the additional problem that the functional significance of these maps in the cortex is not at all clear. So the way that the brain works at the very first approximation is by the connections between neurons, and you could easily preserve all of the connections in the cortex while moving the neurons to different locations, in which case you jumble the map, but the connectivity would still be exactly the same. So the significance of this kind of map is not clear, and the tendency to explain spatial perception by pointing to cortical maps doesn't really seem like a proper explanation. In addition, there are lots of examples where you can have a topographic map which doesn't seem to be associated with spatial perception. So in the ear, the cochlea, the basilar membrane of the cochlea, which carries the hair cells, is projected in a topographic way to the auditory cortex. So there's a map of the basilar membrane in the auditory cortex. But that map is a spatial map, rather like the one I'm showing you here of the skin, but it doesn't relate to the spatial characteristics of how we hear sound, it relates to the frequency. So there's something unsatisfactory about just demonstrating that cortical maps exist if you're trying to explain how we perceive space. And the alternative, which has basically been the dominant model in neuroscience ever since the 19th century, has been to explain space in terms of movement. This is sometimes called local sign theory in psychology. It's not a good name, but that's the name that psychologists think about this as. And the idea that space is to be explained in movement has really been very popular recently, since the Nobel Prize-winning work of John O'Keefe, where he performed these fantastic experiments showing that a rat navigating in an open field has neurons in multiple brain areas, but hippocampus, in particular, neurons which fire when the rat is in one and only one place within the field. So this neuron fires when the rat is about here in the field, and it doesn't fire when the rat is in other locations. So those are place cells. And there are other cells which seem to contain a sort of a grid of the arena, like little nodes on a map at either highly spaced frequency or more widely spaced frequencies called grid cells. So these seem like a kind of an indicator of you're here, or I'm here, and an indication of how far you might be going. So the concept here is that as the rat moves around, it's keeping track of where it is. It's doing a particular kind of spatial perception, namely perception of one's own spatial location within the wider environment. Here's a rather nice quote, just to indicate philosophy and neuroscience, from Gareth Evans. A one-dimensional space may be constructed out of any experience as long as the experience exhibits such order and regularity that its course can be seen as simultaneously due to the way the world is laid out and to the subject's continuous motion through it. Nice, long philosophical sentence. So if you know how you're moving around the space, then, or if you know how you're moving, you can construct a space from your movement. So that's the dominant idea about how space perception works. It's particularly sort of been developed in the context of one's own location in the environment. But the same argument about the relation between space and movement works if it's not you that's moving, but if you're trying to locate objects in the environment that are affecting you. So according to the space equals movement theory, what does it mean for a stimulus to be here as opposed to here? What it means for the stimulus to be here is that the saccade, the eye movement that I make, here I'm making head movement as well to show you, the movement that I make to look at it is different from, and perhaps of greater amplitude, than the movement that I make to look at the stimulus here. So the discriminative feature that makes this stimulus here and that stimulus there, in other words, the difference between their spatial locations, is ultimately represented in terms of the different orienting movements that I make to them. Okay? What's the difference between this location on my skin and this location on my skin? Well, really, the fundamental difference is that if a mosquito lands here, I make this movement, and if a mosquito lands here, I make a different movement. So what allows the brain to understand and to compute the location of stimuli, the location of objects, is ultimately the different orienting movements that we make to look, to touch, to reach, to interact with stimuli on those receptive fields. And ultimately, the fact that we perceive space is reduced to our movements within it. It's the same idea whether you're a rat moving in an open field, or whether, for example, you're trying to look at an object or touch something on your skin. Space ultimately comes down to movement. Now, this idea is old and it's classic, and the idea that space is ultimately related to movement is explained in 19th century sort of foundational texts of psychology and philosophy, always with two examples. One is the saccadic eye movement, and the other is self-touch. Those are the two examples that are always given to explain how you can reduce space to movement and how you can therefore explain space in terms of movement. And self-touch, the example of trying to swat the mosquito which lands on your skin, is widely used, but it turns out there's actually no experimental data on this at all. So the concept that our spatial sense of touch and the sense that we know where objects are when they touch our skin is in the textbooks, but there's no evidence. On the other hand, it's clear that self-touch is an extremely common behavior. This became highlighted during COVID when initially we were all worried that touching the face would somehow spread the virus, and I think now that was discarded, but a number of studies focused on self-touch during that time, and it's extremely frequent that we touch ourselves. I mean, if I look around the room, some of you are sort of passively self-touching, but quite a lot of us are actively self-touching, particularly hand to face. If you want to have an interesting look at psychology on the internet, it turns out that if you type in self-touch, you get some pretty weird things. And one of the weirdest is the enormous amount of effort that goes on stopping children from sucking their thumb. So sucking the thumb is one of the earliest goal-directed behaviors to emerge. It happens in the womb. We all did it for years, and then our parents seemed to go completely obsessed with trying to get us to stop. There's an entire industry on the internet of how to stop your child from sucking their thumb. So anyway, this just shows that self-touch behaviors are really common. They tend to be rather pleasant and self-affirming, and in fact there are lots of anxiolytic stress management techniques. Here's one called butterfly hug, which teach you to hug yourself to feel better, and of course there are lots of industries, particularly the cosmetics industry, which sort of features a lot of this kind of advertising. Now that's all interesting and fine, and possibly related to the C tactile fibers that we heard about just now from Ulf. But what I want to concentrate on is space. So if you touch yourself, there's a very strong spatial correlation between the movement that you make and the touch that you feel. Okay, so if you move your index finger along your cheek, then maybe you're moving your index finger 10 centimeters and you feel about 10 centimeters of movement on your cheek. There's a one-to-one relationship between what you do and what you feel. And in continental philosophy, this has been popular, or not popularized, but it's been discussed in the works of Merleau-Ponty and the touchant-touché arrangement. And this is a really interesting situation because you've got two signals. You've got a movement signal and you've got a tactile signal. You've got a movement signal coming from your arm and you've got a tactile signal coming from your face. And the question is, which one dominates? Which one basically gives you the spatial experience, which allows you, for example, to discriminate a long stroke from a short stroke, a stroke here from a stroke here? Okay? How do you actually produce a spatial percept out of these two signals? Is it that the movement provides basic spatial signals which underlie the spatial perception of touch, or is it the other way around? Does touch have an intrinsic spatial signal that can be used to learn the spatial parameters of movement? So in French continental philosophy, this is basically about whether you are a touchant person or a touché person, or you have a touchant theory of spatial perception or a touché theory. Okay, so the question then is, how do you perceive spatial distance? So this is speculated on a lot in the literature, but as far as I can tell, there's been no experimental studies. So we set out to do an experimental study, and when you try to experiment on basic mental processes in the human brain, you normally try to interfere with them, because you can't experiment on something without sort of tearing it apart. So what we've done is we've built a set of two haptic robots. So these are commercial off-the-shelf haptic robots. And we've coupled them together in a leader-follower arrangement, so that if you move your right hand, then this robot will follow you. This robot this robot is like a handle that you can move. And then this other robot, which exactly copies in a leader-follower arrangement the movements of this robot, will move a paintbrush, which you can see here, backwards and forwards on your skin. So it's a computer-mediated version of self-touch, and you can move your right hand in order to stroke your left forearm. Well, I don't know how often you do that, but sometimes we do perform these kinds of stroking activities. It's much easier to study hand and forearm than hand and face, even though hand and face is a more naturalistic behavior. So I'm going to try and show you a video of how this works. So let's hope that this works. This was working absolutely perfectly before. Can you give me an indication of how to make the video work?
You need to exit the laser pointer.
Thank you very much for that. So, okay. So the person makes a movement of their right hand, and notice how the paintbrush strokes their left arm in perfect synchrony. So what you'll notice there is that there were two movements that you saw, and they were of different sizes. I'll show you that again. So there the right hand movement was rather large. Here the right hand movement is much smaller. Now the critical thing about using this leader-follower robot thing is that we can now program the spatial relationship between what you do and what you feel. So we can program a gain between the movement that you make and the touch that you feel. So we can randomize completely so that you either make 1 unit of movement with your right hand and feel 1 unit of stroke with your left, one-to-one gain, Or we can have, for example, a 1.5 to 1 gain, where you make 1.5 units of movement with your right hand, and you feel 1 unit of stroke on your left forearm. Or we can have a 1 to 1.5 gain, where you make 1 unit of movement with your right arm, and that turns into a stroke 1.5 units in length on your left forearm. So we've broken the normal way that during self-touch, what you do is exactly the same as what you feel. And only by tearing those two things apart in an experimental situation can we work out what actually dominates your spatial perception. Is it what you do, or is it what you feel? Is it the touchant, or is it the touché? So everybody got that by decoupling how you move and the sensory consequences on the skin that you're stroking, we can see which one dominates your perception. There's a lot of technical details here. You never see your hands at any time, so there's in fact a black sheet just underneath your chin so that you can't see what you're doing. The movements that you make are not something that you can choose. You move the right-hand robot backwards and forwards until it bumps against the wall, and you can't predict where the wall is. So you can't decide for yourself how much you move. You move backwards and forwards until you feel that you're stopped. And that stops you from sort of actively deciding what spatial distances you're going to produce. It then becomes something the experimenter can control. The movement of the touch, the movement of the right hand and the touch on the left forearm are completely synchronous. The gain is randomized, so you can't ever learn whether you're in a 1 to 1, 1.5 to 1, or 1 to 1.5 situation. And we have two different conditions. In one condition, which you've just seen here in this video, the self-touch is active, meaning that you move the robot. In another condition, it's passive, which means that you just hold on to the robot and an experimenter moves it for you. So your brain is not actually sending any signals to your hand. You're just being passively dragged about. Okay? Right. So what we're going to do then is have extents, or an extent of movement and an extent of stroking on the right hand and on the left forearm respectively, and we need to ask you to make a judgment about the length of the movement that you made with your right hand, or in a separate block of trials about the length of the touch stroke that you experience. And you're basically just reporting some spatial feature of what you perceive. You're reporting space. In this case, the distance of a stimulus, the length of the line. And you make the report by adjusting the length of a line that you see on the screen. So how do you get people to judge space? That's quite a tricky problem in experimental psychology, but the way we did it is you moved, you felt, and then a line appeared on the screen, and you adjusted the length of the line on the screen using 2 foot pedals until it felt exactly the same as the movement you just made, or exactly the same as the stroke you just felt, and then you said yes. Okay, so we're able to work out basically what spatial percept you have, either of the movement you make with your right hand, or in separate blocks, what spatial percept you have of the tactile stroke that you feel with your left hand, and we're able to decouple those by programming the gains. Okay, this is a rather complicated slide, so I'll take you through it rather slowly. I'll try and show the pointer again. Okay, let's just look at this top left-hand plot here. Just look up here at the top left. What we're showing here is a plot of the actual distance of a tactile stimulus, which we varied so that it was sometimes 4 centimeters, sometimes 6 centimeters, sometimes 8 centimeters, and you could not predict. So we varied the length of the stroke that you felt. And on the y-axis, we're showing how long you thought that 4 or 6 or 8 centimeter distance was, as reported by the length of the line on the screen that you adjusted so that it looked just about as long as the stroke that you had felt. So perfect perception would be a diagonal line with a slope of 1. Okay? And what you can see here is, if you look at these data points, you can see that on the whole, as the actual distance of the tactile stroke gets bigger and bigger and bigger, people perceive it to get bigger and bigger and bigger. These lines go up. So that means people perceive tactile spatial extent. The other thing you'll notice is there are actually 3 lines here. And these 3 lines correspond to the 3 different gains that we can set on the robot. The middle line corresponds to the one-to-one gain. So that means that in order to stroke yourself 4 centimeters, you had to move 4. In order to stroke yourself 6 and 8 centimeters, you had to move 6 and 8. The light line corresponds to the situation where you have to make a very big movement to deliver the tactile stimulus, and the solid line to where you have to make a very small movement to deliver the same tactile stimulus, because we've changed the gains on the robots. Now, you're actually asked to judge the touch. You're asked to completely ignore the movement and just judge the touch. Just tell me how long the stroke was. Doesn't matter how far you had to move to make it happen. Just tell me about the touch. So if people could just report this, if people just had tactile spatial perception, then it wouldn't matter what the gain of the robot was, and all these 3 lines would be exactly one on top of each other. Because it wouldn't matter how far you moved, you're only asked to report how long the stroke was. So the fact that these 3 lines do not overlap, which is indicated by the big red arrow here, shows that when you ask people to judge touch, they're using information from movement. When you ask people about the stroke that they feel, they're actually using information about how far they move to produce it. They can't perceive touch independent of movement. We can do exactly the same thing in another block of trials where we could say, how far did you move the robot? And we can set up the robot so that their movement was 4 or 6 or 8 centimeters, and they'll adjust the length of the line on the screen. But the critical thing is that we programmed 3 different gains between the 2 robots. So the solid line is where the gain is 1-to-1, and the light line is where, when you move 4 centimeters, you produce a 6 centimeter touch. When you move 6 centimeters, you produce a 9 centimeter touch, and when you move 8 centimeters, you move 12 centimeter touch, because the gain is set to 1.1 to 1.5. The solid line is where the gain is set to 1.5 to 1, so when you make a given movement, you experience a tiny touch. If you could perceive movement without any reference to touch, all these 3 lines would exactly overlie each other, because you'd be judging the movement that you make and you'd completely ignore the touch that you felt, and you can't. These 3 lines are all spaced out. That's what's indicated by this red line. So, and we can do this both for when you're making active movements, that's these top 2 plots that I've shown you here, and we can also do it for when you make passive movements, when you simply hold on to the robot and the experimenter moves it for you. On the right here, what we're looking at is how much you're influenced by the unjudged event, how much interference there is from movement when you're trying to judge touch, and from touch when you're trying to judge movement. And 0 would mean that you can perfectly judge what you're supposed to do and ignore the influence of the other thing, and 1 would mean that when you're trying to judge touch, you're actually completely dominated by movement, or when you're trying to judge movement, you're completely dominated by touch. So you can break apart touchant and touché. You can break apart the fact that in normal self-touch behaviors, the movement and the touch always agree. And what you find is that the coefficients here are really big. They're about 0.5 to 0.3. So people are really, really strongly influenced by movement when they're trying to judge touch. That's these 2 numbers. And they're really, really strongly influenced by touch when they're trying to judge movement. So people struggle to perceive the spatial distance of movement and touch independently, and there's a very strong crosstalk between the 2. Now, the prediction that comes from space equals movement theories, the prediction that comes from the idea that ultimately we perceive space with reference to the way that we move through it. We perceive event space on our skin with reference to the movements that we make when we touch ourselves. What they would predict is that you would get very, very strong influence of movement when you're judging touch, and no influence at all of touch when you're judging movement. So this would be the prediction of space equals movement theories, and that's clearly not what we get. I'd like to just tell you about one more experiment, and then I'll stop. So, how do we learn to perceive space? So the standard way in psychology that we study this is we study what's called adaptation paradigms. So first of all, what we're doing here is we're getting people to judge the tactile extent of a stroke, which can be either 4 or 6 or 8 centimeters, and they'll do this for a number of times. And then we'll have, and that's with a gain of 1-to-1. Then we'll have a learning phase where we'll change the gain. So now 1.5 units of movement produce 1 unit of touch, and then we go back to a post-test. And what you find is that changing the gain during this adaptation phase produces an after effect. So after people have learned a new relation between movement and touch, you see an after effect of that, and the post minus pre is taken as an index of learning. And what we can see here, let's just look at this one column on the right. So this is the case where you're judging movement, and we've changed the gain so that a small movement produces a big touch, 1 to 1.5. Movement to tactile gain is 1 to 1.5. And there's a highly significant after effect here. So adaptation to an increased extent of touch produces an after effect that makes subsequent movements feel shorter. If you make movements which produce big tactile strokes on your skin, and then you go back to normal, then your movements don't feel the same and they feel shorter. This is a classic cross-modal after effect. And it proves that touch updates a model used for movement perception. So this implies that touch is really important for telling us about the spatial extent of our movements. And that's exactly the opposite from what space equals movement theories say, because they say that movement should calibrate our sense of touch. So here are some conclusions which you can screenshot if you want. I think space perception begins with the body and then spreads to the external world. I think touch may be an intrinsically spatial sense. And classical ideas of motor dominance in spatial perception may be oversold. Self-touch behaviors like grooming involve self-discovery and self-model updating and self-affirmation, as well as self-cleaning and self-therapy. Thanks to all these people who did all of the work. Thank you.
So at the end of this, we're going to wrap it up in the two, we're going to wrap up the collaboration, and what we're going to do is have questions here in Hamburg, and Barnaby will lead questions for Patrick in Oxford. And our final talk this evening is going to be the philosophy talk, and we are so pleased to be able to have with us here in Hamburg the Wilds Professor of Mental Philosophy from Oxford, Professor Michael Martin. He is the Wilds Professor, which is a professorship held jointly between the Faculty of Philosophy in Oxford and the Psychology Department in Oxford. So it's a very unusual appointment, and he has expertise in these two areas. So he is ideally placed to speak to us tonight. It also happens that Mike Martin's research interests have to do with sense perception. And his talk tonight is entitled Philosophy Field Studies, which I find deeply intriguing. So Mike, tell me what it means.
I didn't put, I think it's indicating that I'm a philosopher, and it says philosophy, title field studies, and it's just a bad one. So I'm carrying on really from an aspect that Patrick raised in his talk when he was asking in what sense is touch genuinely spatial? And really what I want to ask here is to raise a potential contrast between ways in which vision is spatial and touch is spatial. And at the end I'll come back to a question that Patrick's raising in his work, where he's asking really about the spatiality of touch across the skin, and say whether the question he's raising raises problems for the contrast that I'm going to suggest. So kind of anticipating where I want to get to. Kind of background here is to ask, how do we contrast vision and touch? And at the beginning of this evening, I need to emphasize that we tend to focus, at least if we're sighted, on the case of vision. I mean, one of the ways of really looking at this, if you look at publications in the neurosciences about vision versus any other sense modality, well, you can get buried day by day in the number of things that are published. Whereas if you look at what is published about the nature of tactual perception, it shrinks. And it really strikes me that when you look at survey material about the nature of, for instance, haptic exploration. Still, the key publications take us back to the late 1980s, when I was a graduate student and first looking at these questions. So vision kind of focuses the mind for sighted human beings in the way they tend to ignore touch. And philosophers are among the people who exhibit this cognitive perception. They almost invariably have vision in mind. So there's a nice question. Well, can we generalize from the visual case to other senses? And do we think that visual spatial perception is the model for tactual spatial perception? And so today what I want to suggest is that there's a contrast in the way in which space enters vision and touch, which is not a simple one of spatial content in the sense of the information that we gain about the spatial properties or relations of objects via vision and touch, though obviously there are different levels of resolution, so there are contrasts to be drawn. Nor yet should we think of this in terms of the distinctive quality that is, say, what it's like to see versus the distinctive quality what it is to feel, which is often a kind of catch-all that philosophers like to appeal to when they want to indicate that they're specialists about consciousness. So you can't really see it. I hadn't. Rather, the suggestion that I'm going to make is that there's a contrast in the way in which we experience space in vision and experience space in touch, which is structural. Specifically, I want to suggest that, at least in normal vision, so this won't apply to normal vision, a region of space is given to us as kind of an enclosure, a field within which objects can be located. But when we think about touch as it relates us to the external world, contrast this with the surface of the skin, there's no analogous tactual field for the sense of touch. So I want to affirm, at least as we ordinarily think of our experience of touch, that our experience of touch is spatial experience, but the distinctive way in which we think of vision as having a field, touch doesn't have a field in that way, and I want to explain that in a little bit more detail. Now, just to clarify, I'm not questioning, I'm not taking a stand one way or the other, whether we should think of our skin as providing a two-dimensional touch field. Patrick has work indicating ways in which there may be such, and how spatial information can be extracted from coding which is fundamentally not spatial. And the claim that touch doesn't have a tactile feel is not seeking to contradict that or speak in any way. It's rather the suggestion is that through touch we learn of objects in space around us beyond our body, and when we learn of those objects, we don't locate them within a sense field. Now, the contrast and the overlap between sight and touch has long been an obsession for both philosophers and psychologists. And philosophers, when they start talking about this, tend to go back to the 17th century and the Irish philosopher and physician William Molyneux, who famously raised the question whether a blind man, now sighted, can recognize what he knew by touch as a cube or a cylinder, whether he can recognize them now by sight. So what the correspondence between the senses are. Now, there are lots of background different assumptions that philosophers and psychologists can have in mind when they're interested in whether the answer to this should be positive or negative. Indeed, one of my predecessors in the position I now occupy what was then the wild readership, rather than professorship, in mental philosophy. His final publication was a long essay in which he basically suggested that none of the philosophically interesting questions get settled by finding the empirical result, whether it's yes or no to Molyneux's question. But I want to pursue much of the debate about Molyneux's question, focus on an assumption of a dissociation between sight and touch, and skepticism of whether there was a common spatial world that they gave us access to. Whereas the question I want to raise today takes as its assumption in the background that they do coincide on a common world. Now, in the visual case, we have at least three notions of field that you could play with. So you might think, look, we have receptive fields on the retinas where the spatial relations among the receptors is exploited functionally to derive spatial information about stimulus. So I think it's because the receptors themselves are spatially organized in a way that is functionally significant that it makes sense to talk about field. On the other hand, working inwards out, you might say, look, visual experience, visual sensation is one of the things that we think of as inherently spatial, except in the case, say, of tunnel vision. And many philosophers and some psychologists are inclined to think there's a kind of spatiality to visual experience, independent of its objective significance. So you might think there's a kind of pixel map of visual sensation. And you might, in talking of the visual field, have that in mind too. But actually what I want to focus on is a third notion, and that's the idea of a volume of space within which we locate the objects that we can see. So that I want to suggest it's not just that we learn about the spatial location relation of objects around us, but that we typically experience them as inhabiting a larger space that in some sense we also experience. So, consider these two stars. You see the spatial location relative to your viewpoint of each of these stars. You see the spatial relation of each star to the other, but the light blue one, because it's kind of white in this screen, is to the left of the red star, for example. I think you also see the stars each in a location which is a sub-region of a larger space that you also see. And the stars are enclosed within a larger space which is itself seen. So you see the space between the stars and not just the stars. And one might say of these other regions, even if there's nothing interesting in them, they're all possible locations for things that you see. But there's a sense in which there's a space seen as well as objects located within it. I want to contrast that with the case of touch. So take a simple case of tactile awareness. You might, for example, here we're not treated with evil alcohol at the moment, so you don't have wine glasses to hand, but if you grasp a wine glass by the rim, even without looking at it, or if you run your finger around the rim of the glass, both of those cases are ones in which actually you can come to be aware of the shape of the rim. In the first, even with your eyes closed, you can come to be aware of the circular form of the rim. You have regions of tactile sensation, the pressure points on your fingertips in contact with the glass, but you're also aware of the rim extending beyond these points, and the rigidity of the glass resisting the muscles of your hand play a role there. So there's a sense in which you're aware of the rim of the glass extending in space, but there's a sense also that you're not aware of those bits of the space that go beyond parts of your body. Now, in the case where you have kind of active touch, active exploration, you keep track of the route you traverse with your finger through your active exploration and your awareness of the disposition of your finger and hand. And of course, kind of standardly, this is a case which is really active touch, but in fact you can do it passively too, and it's unclear in the passive case that you're not equally able to discover the shape of the object. So active touch probably does give you an advantage, but it's not essential in this case. So again, there's an interaction between the rigidity of the glass and the force applied through the muscles of the finger. But again, I want to suggest there's a sense in which you're aware of something in space which goes beyond anything that could count as an immediate object of awareness. In a way we might say this, we feel sensation within our own bodily limits. So wherever you feel sensation to be, it feels as if your body extends to that place in space. I mean, if you go back to the 1980s, Ulf mentioned earlier about the plasticity of our sense of our body. J.R. Lackner did some amazing experiments in the late 80s using vibrostimulators to illustrate how plastic our sense of the extent of our body is. So much of the information about the disposition of our limbs comes from the spindle receptors in our muscles. So if you stimulate those receptors without exercising the muscles, you can get various kinds of illusions. For example, with a subject with eyes closed and finger on the nose, you can create the illusion that they've extended their arm. And then you can ask, how does your nose feel? And the answer is you get Pinocchio effect. It feels as if your nose is extending out with your arm. And if you do the reverse experiment so that it feels as if they're pushing their arm back through their head, they have the sense of their nose collapsing into their scalp. So there's sort of plasticity in the sense of the extent of our body, but still I want to suggest we have a sense that our body is limited in as much as we have a sense that space extends beyond wherever we feel. And we locate the object of touch as lying in that space which lies beyond the limits of our skin. Now, in connection with this, Thomas Reid, in his inquiry, famously contrasts sensation with perception, this is in chapter 5 on touch, by focusing on an example of touch. He asks the reader to press their head against a cold, hard surface. On the one hand, one can feel sensation, something related to how one is oneself, and on the other, one can feel the hardness and coldness of the marble, something that lies outside of one. Now, Reid wants this to be a contrast between something subjective, sensation or feeling, and something objective. So just as all of your introductory textbooks are called sensation and perception, he calls sensation the thing that's on the inside and perception the thing that's focused on the wall. But I think we can think of it in another way. When I press my head against the surface, I can now tend to have things feel within my body. The sensation is bodily sensation, interoception, as we can say, of the state of my forehead. On the other hand, I can attend to what lies beyond my body and evokes this sensation. I can attend tactually to the surface of the wall. And I think this evokes the picture of tactual awareness, which was initially proposed by the late Brian O'Shaughnessy, that I use my body as a template to explore the spatial, textual, and dynamic properties of my environment. Now, to go back to what I was saying earlier, we think of vision as providing a container within which spatial locations and objects at such locations fall. But in touch, we think of the body as a volume within which there can be sensation or awareness, and the space of tactile objects as being that which lies in the same space as the body, but extends beyond it. So here we have two stars again, but instead of thinking of them as stars, think of them as cracks on the wall. So suppose you're a wall climber, my grandson is one such. A wall climber may feel two cracks in the wall separated just as the stars are. They sense the locations of the cracks and the relative position of the cracks to each other. But the space in which they locate cracks includes regions of which they have no current tactile awareness, namely the region between the cracks. And so that, I want to suggest, is the contrast between the visual case and the tactile case. Now note that this difference between touch and vision is not simply one of spatial information, what one knows about the location of the scars or cracks, nor is it well expressed by talking of different qualities of visual and tactile experience. Rather, it is a structural difference in the way in which space and spatial properties and relations are given to us. Now, if we accept that idea, then the question that Patrick was posing for us in his talk is central to thinking about this. Because Patrick is partly concerned with the question, can we start with something that is not in itself inherently spatial, but learn to extract spatial information from it? So likewise, you might think, look, as I told it, you can extract spatial information in touch without being given a space, in the way in which vision gives you a space, as well as information about the spatial objects there. But how do we get to be given a space rather than just information about spatial properties? The mere fact that the retinas are spatially organized, as Patrick was emphasizing at the beginning of his presentation, really does not explain the way in which vision is inherently spatial. So if there is really such a structural difference in the way we experience space between vision and touch, what can be the functional ground of that? That question, I'll draw it to a close. Thank you.
Sign off as I said we would do. I wonder if Patrick wants to respond to Mike. Patrick, is there anything you'd like to say?
Thank you. That was really interesting, Mike, and I'm sorry that we haven't got a chance to debate in more detail, because we've had these discussions over many years now, and they're always really thought-provoking and really important. So I think I enjoyed your presentation a lot, and the thing which comes to mind is that the examples you always give are multiple fingers on the wine glass, multiple hands on the climbing wall, and they're what might be called sparse sampling. You get tactile information at a few isolated points of your body which are in contact with the external environment, and what you're suggesting is that you need to fill in between the sparse points of actual sensation in order to have true spatiality. And that's absolutely fine. That's a really interesting theory about spatial perception involving the representation of the unsampled locations. But it's not the only kind of interface we have with the world, because sometimes we might want to think about the body not just as having a few grappling hooks that contact the world, like the 5 fingertips or the 2 hands on the climbing wall, but rather as more like the retina, more like a continuous sheet which is stimulated in a way which, in my view, supports a field, at least in your second sense. So in the case of a stimulus that's moving across the skin, you have the successive stimulation of one receptive field after another, and you have some of them being activated in a particular temporal order. So not all of them are activated, it's still sparse, but there isn't quite the same sense of filling in. So I think that is one important difference which has not been sufficiently considered in spatial perception. I think the only other response that I would make is I'm struggling to see the difference between your second and third sense of field and the idea of 2D versus 3D. So I agree that there are multiple spatial dimensions, and I agree that touch is perhaps naturally thought of primarily as a two-dimensional sense, and I agree that there's a physical world where we want to think about objects as having three dimensions, and touch, obviously as a 2D sense, won't give you the third dimension. Are you saying more than that? Thank you.
Thanks, Pat. Yeah, I have learned a lot from what you have to say about thinking of the spatiality of touch across our skin. And I really didn't take anything I was talking about today to be in conflict with that. In relation to the question you just raised, what I had in mind with the second sense of a visual field, I was being neutral whether it had any application to touch or not. And in part what I had in mind was the way that philosophers are inclined to think visual sensation might still have an inherent spatiality. George Berkeley's term for it was extensivity. Even independent of its interpretation in respect of the objective environment. And so sometimes in the philosophical literature, you find philosophers supposing that if you're talking about a visual field, then that shows that you're committed to something like sense data. And so what you're hopefully calling, in the case of touch, anything that you would take to be analogous to a sense datum or a sensation would itself be located either on the skin or within the body. And so to be an object of touch would lie outside of that. So even if there are 2D sensory fields in both vision and touch, they'll project into the
Ulf, is there anything you wanted to want to say in this connection? Do take the microphone, because I think we can hear the speakers back and forth, so it would be good if we just give them a moment.
What I was thinking about, what is crucial difference between the visual representation of objects and the tactile space, whatever that is that vision is a far sense, and the tactile sense, of course, requires that you're in direct touch with your surrounding, and so there should be some difference in scale somehow, but perhaps also conceptually. I was especially intrigued by the idea that when you have your head leaning against the wall, or an object in your hand, that in a way your body surface is, well, extending around the object. So you can ask yourself, is in fact the object becoming a small part of your body, or is there still an edge between your skin and the object? So it's the human tactile representation, or the tactile field like an amoeba surrounding, well, small objects that you integrate into your personal shape or into your body map. So that's intriguing questions.
Mike, did you want to say anything in response to
that? Well, I would have thought that the most obvious cases where there's a case for saying you get integration are where you get projection of inner sensation in the use of prosthetics, for example, and there you do get extension of the body map. But I take it in normal haptic exploration, you're not assimilating. You're not like those who use a switch know about Kirby, where Kirby swallows something and takes on the characteristics of whatever he's swallowed. So that seems to be Ulf's image of active touch, and I think it's not normally like that. And also just, I think, very slight qualification to something you said earlier. You said, look, sight is a far sense, which seems entirely right, but with touch you always have to be in contact with the thing that you're aware of. And that's, that might be slightly misleading in the one of the ways, particularly with haptics, we can be aware of things where the relevant part of the object we get to be aware of can actually be quite distant from our body, because we can exploit the dynamic properties of an object. So you can learn of the center of mass of something by manipulating a rod, for example. And the center of mass of the rod need be nowhere close to your body for you to do that. So the idea in which it has to be close is just there really has to be physical interaction between relevant properties of your body and the object that you learn of through touch. So touch is a mechanical and contact sense, which is exploiting the correspondences in those properties to the objects we explore in our body. And that's not, there's no analog, or that's not the primary analog of how we're extracting information with vision.
Okay, thank you. Patrick, I'm going to give you one more opportunity. Is there anything you'd like to say?
No, I'm fine.
I'm fine. Or
thank you.
shall we go our separate ways with the audience questions now?
I'm fine.
Patrick? I think they may have already switched off. Oh, sir, have you switched off?
No, we haven't switched off. No, it's been very interesting, but I have no further comment between Oxford and Hamburg, so thank you.
Okay, excellent. All right, I think what we're going to do now is Barnaby is going to take questions for Patrick in Oxford, and I'm going to take questions for the two speakers here in Hamburg. And I'm going to say goodnight to Oxford, and with apologies again for some of the technical glitches that we had, which I did predict in my introduction. And I hope that you will all continue to look at the website on Eventbrite and attend in Michaelmas term, where we will be coming back with something that we have not decided yet, but we will put it up on the website over the summer, and you can have advance warning that way. So please put the date in your diary, and I hope to see you in Michaelmas term. Good night, Oxford.
Let's go. Just us. Thank you very much for your patience. We have about 10 minutes to ask Patrick some questions. Fortunately, as you have already witnessed, he's quite an expert in all of these fields, and his work is sort of interest across the disciplines. So hopefully he will be able to field any questions that may have arisen throughout the three talks. So are there any questions? Good. Well, shall we start right in the front?
Yeah, I found all this extremely fascinating. Now, it brings to mind questions about vision, visual impairment, and touch that perhaps, and space, which perhaps go a little beyond the Molyneux question. I'm bringing it up as somebody who's interested in numerical and mathematical cognition. That probably applies to many things. So spatial ability is generally found to be quite important to mathematics, and many people who study mathematical cognition refer to it as visual spatial ability, but in fact there have been studies by, for example, Julie Castronovo and colleagues, which indicate that people who are blind from an early age often do very well in certain numerical tasks using alternative routes to spatial representation, possibly gained from movement, for example. And of course, touch is very important to visually impaired people. And I was wondering if you had any comments about the use of alternative routes to spatial knowledge by visually impaired people, and indeed by sighted people under conditions where vision is made impossible, very dark conditions, for example, and to what extent you would think that this is fundamentally, the spatial awareness under such circumstances is fundamentally different from what is gained from vision.
Okay, thanks for the question. I'm talking completely out of area, and I'm really just speculating. But I think the research that I described suggests that simply having skin with receptors in the absence of any other sensory input, and in fact in the absence of movement, is sufficient to allow you to perceive extent. So extent, how long, how big is something, how long is a line, that seems to me the key feature of space. If you go back to the sort of ideas of Euclidean geometry, if you can't perceive an extent, then you can't really get space at all. If you can't tell that one distance is bigger or smaller than another, you won't get started. If you can tell that one extent is bigger or smaller than another, if you can operationally perceive extent, then you probably have enough to support numerical cognition. So as you know, the idea of the number line, which is taught to children and which is thought to be the key sort of construct for the sort of spatial notion of number, my research suggests that you could get a number line on your skin. There might be a lot easier ways to learn mathematics than tracing out lines on your skin, but it's a support that is there. It's sufficient to bootstrap some sort of perception of space. It would be interesting to see whether it could be used in sort of sensory substitution and in teaching numerical cognition. I think there's a really interesting question about the respective roles of movement and touch. So we often instruct children, for example, to move their finger along the number line in order to understand why as they count. And there's a very nice example in the work of the philosopher Jean Nicot, where he constructs space by imagining a ladybird on a piano keyboard, which hops from one key to another, and as long as it can count how many times it hops, and as long as it can recognize the sound made by each piano key when it jumps on it, according to Nicot, it can construct spatial perception. That's again this question about whether you need to move in order to be able to get space or not. And I think perhaps you don't. I think simply being a passive sentient creature might be sufficient to give you spatial perception, and in that case it might be sufficient to give you numerical cognition as well. That's the speculation.
Thank you very much.
Thank you. I think Roger was next.
Thanks. Yeah, thank you for your talk. Does this work? Yes. In your answer to Mike, I think you said, did you correct me if I'm wrong, made a contrast, was it a contrast between touch being, I think you said, two-dimensional. Did you say that?
Well,
yes.
The skin is two-dimensional, and Mike is very interested in the representation of the object that you touch, and the object is three-dimensional in the case of the glass.
I just wonder if that apparent puzzle is a puzzle, because often if you're grasping a tube, you might think, the tube is three-dimensional, but my skin is one-dimensional, two-dimensional. How on earth can I get from one to the other? But of course, if you grasp the tube, your hand is making the shape of the tube, and it seems that if you're going to call the tube cylindrical, you might as well call the shape of your hand cylindrical. But I say the tube, the surface of the tube, like your skin, is two-dimensional, but that seems irrelevant.
Yeah, no, that's really interesting, and there's I'm not going to try and answer it myself. I'm going to take what I think is the dominant way that Mike and others in the field think about this. So physiologists distinguish between two different kinds of bodily sensation: skin sensations and muscular sensations. So inside your muscles, as well as being motors for contracting the muscle and actually moving, there are also sensory organs called muscle spindles. And the muscle spindle sends a signal to the brain saying how long the muscle currently is. So, for example, the muscle spindles in my biceps will send a signal that my biceps is being stretched as my hand moves forwards and as I extend my elbow. So the muscle spindle signal probably plays a key role in the brain knowing where all the bits of my body are. This is called proprioception. And one of the most interesting features of touch is it only really works well if you combine it with proprioception. So the nice example that Mike Martin gave of feeling the roundness of the wine glass, or feeling the shape of the wine glass, that can't come from touch alone, because all that touch gives you is these 5 sparse points. But it can come if you combine the fact that I know this finger and this finger and this finger and this finger are all touching a sort of a cold, smooth object, with the fact that I know where my fingers are, I know the disposition of my fingers in space, I know the postures of my fingers, I know the location of different bits of my body. So I think the 3D part and the volumetric perception of objects and the recognition of shapes and so on, I think that basically comes from proprioception, from muscular sensation, and not from skin sensation. That's pretty much the argument that Mike's examples of the climbing wall and the glass point to. So a similar argument is developed by Matthew Fulkerson, I think, in a recent paper. So when we have an awareness of objects and their shape and and we recognize them, for example, through touch, we're actually using touch plus proprioception. And I think a lot of what Mike is talking about really reflects the fact that the skin alone gives us, at best, a very impoverished representation of objects in the sort of Newtonian or everyday sense. Whereas if we can move our skin about and, for example, explore an object, then we can build up a rather rich 3D representation. But when we do so, we're combining skin sensations with proprioception. There's a long tradition of looking at how, for example, you recognize objects with your eyes closed, right? So you can find if you put your hand in your pocket and you're trying to separate your bike key from your house key, you can do it even though you can't see. And you do it basically typically by following the contours of objects and by identifying their shape. So that's really interesting. It's really important. It's probably extremely important for blind people. In fact, we know it's extremely important for blind people. But to work, you've got to combine skin sensation with knowledge about where the bits of your body are with proprioception. So I think your example of perceiving the shape of a tube is a really nice one. I think skin sensation will give you the surface of the tube, but you'll need proprioception to work out that it's a tube rather than, say, some other kind of ellipsoid. In everyday life, touch and proprioception always work together. In the cortex, they're kept separate in the first cortical areas. So when the signals from the muscles and from the skin ascend from the spinal cord to the thalamus to the primary somatosensory cortex, as Ulf showed, they're initially kept in separate cortical columns. So the touch and the muscular information are not combined. But as soon as you leave S1 and you go to the next stages along the processing pathway, you get lots and lots of neurons which will respond either to a movement of a joint, which means a lengthening of a muscle, or to touch on the skin around the joint. So touch and proprioception get brought together quickly at relatively early stages in the cortical pathway. And once you get up to the bits of the cortical pathway which allow us to recognize objects and to work out whether it's a Yale key or a Mortis key, a bike lock key or a house door key, then the touch and the proprioception seem to be very, very strongly integrated. So that's I think, clear it's the way that touch is useful given that we can move our bodies. But Nevertheless, I think there is some kind of proto-spatiality which exists even within the 2D space of the skin. And that's what I was trying to discuss. Sorry for the long answer, but a really, really interesting point.
Right, so I think we have time for one more question. So
maybe two short ones?
Maybe two short ones. Two short ones we can also do.
You go first, please.
I have a very
please,
short
you go
one.
first. Oh, yeah.
It's kind of half-formed. It's more... yeah, so we spoke about this, I think it's quite linked to a lot of the previous question about proprioception, and it's being able to see the space between objects. We can both we can feel that, we can see that, and I was wondering to what extent can we really, and I think we were talking about it in the in your talk, or one of your talks, to what extent, like, can one person really experience touch and sight as different things? Like,
right.
can they?
So if I can just see if I can answer that bit.
Yes.
There was an interesting pair of words that might use sensation and perception. Mm-hmm. And you often think about sensation as being a raw and uninterpreted feeling or experience or quale. Whereas perception is often used for the fact that we experience objects and we live in a world of objects, and we don't just have blue flashes, but we see the tablecloth. We don't just have sensations, we recognize the glass and we recognize that the glass is fluted. So that's what the brain is doing. The brain is parsing the blooming, buzzing confusion of all of the receptor stimulation that it receives action potentials from, and it tries to work out what's out there, and the brain is looking for objects, the brain, or trying to feel for objects, so it's trying to categorize what is the source, what is the object which is the source of this current input, and that process is called causal inference. You're trying to identify what is giving rise to the action potentials that the brain is currently getting, and the brain has learned to do that. And it does that in a way which doesn't really respect the separations between the sensory modalities that we tend to use when we teach
they are the same object, so it's just...
Same object, yeah.
You're different,
Yeah. Looks like a glass, it feels like a glass, maybe it is a glass.
Thank you.
There's another question there.
Hi, just a quick question. So you sort of talk about learning about your spatial awareness, spatial perception from how your body extends into the world. So I was just wondering, how does that affect children when they're growing, and how do they perceive differently as like physically how they extend into the world changes? Like, are they constantly recalibrating that 1.51, or is it more difficult?
Yeah, I mean, they must presumably constantly be learning the relationship between the different signals that they send out in the world when they move and the different things that happen, the different afferent signals that come back. That starts long before the child is born. So thumb sucking, I think, is a really interesting behavior. It emerges from around 12 weeks. And I think the initial object that the child learns to perceive is its own body. It lives in a very, very visually impoverished environment, but a rather rich tactile environment before birth. And I think the whole process of sometimes called baby babbling, the seemingly random movements that you see of a newborn infant producing, I think part of what may be going on there is working out the relations, for example, between motor information, proprioceptive information, and tactile information. And once you've got that, you've got a fantastic multisensory space where you can perceive regularities, and you can perhaps represent your own body first and foremost, and then go on to represent the objects in the outside world.
Perfect. Thank you very much. Can we give a big round of applause to Patrick?